So we're here at 127, and we're going to talk about format strings today. I don't have any eye clickers. It's really just one long demonstration. This one is kind of annoying, but very important. It's very easy to take over machines with format strings, and it shows you quite a few important techniques. And next week we've got a guest going to talk about cyber war. He is an authority on the topic. That should be fun. So let me just start out with the slides about format string, and then I'll start demonstrating it. This is chapter 4. Should be right there. Good. I'm going to need this before long. All right. So, get this thing to quit griping. All right. So, get rid of that and do that. All right. So this is format string bugs. This has been around for a while. I think at least 10 years. And it's, again, like buffer overflows, a consequence of very strange behavior of C. The fundamental problem here comes back frequently to be useful to utility to hackers, which is that all you have in the computer is a bunch of ones and zeros. There is no label anywhere that really tells the computer or the human what that data means. So the same file could be an executable code or an image or anything else. And there was a kind of fun demo I saw about a year ago when you open Notepad on Windows and you type in about 20 random letters, and then when you double click it, it runs as a file and prints up an insulting message about the president or something. Because the same pattern of bytes can be interpreted as an executable file or as a bunch of Notepad. Anything can be interpreted as a bunch of Notepad bytes. So anyway, that's the game. Since you don't know what the data means, there are conventions where you try to put extensions on the file name or header bytes or footer bytes, but all of those have a chance of failing. So this is particularly true in C. So if you're in C and you print things out, like I've got I is 1, J is 15, K is 30, so I print them out here. When you print things in C, you are supposed to put a format string before it, which tells C how to interpret it, because this is just a 32-bit number that could be interpreted different ways. So %D says print it out in decimal. %5D says print it out with 5 spaces of decimal, so expand it as necessary. %X prints it out as hex. So when you run that, here's %D, 11530. Here's %5D with 11530, each one of them spaced out to have enough room for 5 digits. It's padded with spaces. Here it is in hex. So 15 is F and 30 is 1E. Here it is in hex, padded to 8 characters long with %AX. Here it is interpreted as a character, ABC. Here it is interpreted as character, and the same bytes interpreted as integers in base 10. And on you, here's a string. A string will just print all the characters until it reaches a null terminating byte. And here's this HG that will actually print pointers, interpreting as addresses pointing to memory. And here's, so with no arguments, this is the one that really gets screwy. And let me do this one live. So here, here's the basic program we're going to attack here. If I nano, see that's pretty good, or fs.c. All right, this is the basic program that has the format string vulnerability. So what this thing does is it takes the name of the program, fs, and then another command line argument. So that's this int argc char star star argv. The argv is the array containing the words that were put on the command line. So the first one is fs, the name of this program. The second one is argv1. That's copied into a normal variable buff, and then you just print buff. And this is why, I don't know why they even allow this. If you asked me, I would have said this is a format error, don't compile. But that's not what happens. You can print buff alone, which includes just one quantity. It should have 2 strings, a format string and then a variable. But it's got just one. And that buff comes from the command line. So I can print anything I want here. So if I run this, guess that's visible enough, fs, hello. It prints hello, okay? But if I do fs %x, it prints a random hexadecimal value. Now, why does it do that? If you print %x and there's no variable, C, in its wisdom, just takes the next value on the stack and prints it. So this is information disclosure vulnerability. If I put a bunch of %x's here, I get a bunch of bytes from the stack. Now that's pretty much messy and hard to read, but you can put in delimiters if you like to make it easier. I can put dots in. Okay, and I guess I want a lowercase x. All right, and so those are the 4 bytes on the stack, wherever this print command is. So I can go as far as I want reading the data on a stack, and this is already something that could very well be quite important. You might find something important on the stack, like a password or something. But it's even more fun is you can write to the stack. And this is because there not only is there %x, which shows you values in hexadecimal, there is %n, which is one of the strangest things in C. Yeah?
So are you popping the stack when you print this, or are you just reading the stack out?
Just reading it, not popping it.
Okay.
So, because what happens is, you can understand how this works if you look at the assembly code. In fact, let's just do that. If I GDB of fs, it's easier to understand why if I disassemble main. Okay. So here's what this thing does. It does a string copy, which takes the data from the command line and puts it in a string variable, and then it calls printf. But remember how printf really works in assembly. You're going to print something. Before you print it, it figures out where it is on the stack, and it pushes that pointer on EAX. So the whole point of printf is it's a function with parameters, and the parameters are just in a row on the stack. So it is doing, if you call printf without preparing the stack properly, it will just attempt to interpret whatever's on the stack as what it has to be to print it. So this is actually kind of natural in the world of assembly. When you call printf, what printf does is go to the stack, find the parameters, and print those parameters. And if you didn't populate it with logical parameters, that's not its problem. It just takes whatever's there and interprets it as a series of parameters to print. So that's how it works. And so the one that is very strange is this %x thing. So I did this one. This shows, %x shows you contents of the stack, but %n writes to the stack, and it writes to memory. See, this reads the first, second, and third, fourth item on the stack, and there they are. If I were to change this to a %n, it would take this number, interpret it as an address, and write to that address. And what it writes is the number of characters that have been printed so far. I have no idea why they did this. It seems to me like it must have been something of use in trying to format things on a screen or something at one time, but that's what it is. So if I change the last %x to a %n, it is going to try to write to this number, 252E7825, which is some crazy number, not at all permitted, and that's going to crash the system, because it tries to write to some number that is not in the address space allocated to this program, and you get a segmentation fault. So now, at this point, I had an information disclosure vulnerability, where I can read things without regard to whether I'm really supposed to be able to see them or not. Here I have denial of service now. Now I can crash the program. So of course, the game is to very carefully control the write. Now in order to control the write, I need to control some value on the stack, because this is used as an address for that write. So if I can control any of these things on the stack, I can put it there. And for a very simple case, this turns out to be pretty easy to do. So let's put 4 A's here. Now remember, if I don't put anything else with just 4 A's and run it, it's going to print the 4 A's. Okay, but if I put this other stuff here, %x dot, %x dot, %x dot, %x dot, put a few of them there. Okay, so here's the A's that I printed. Then comes junk, 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 and there's the A's. See, the A's I fed in here did go on the stack. They're in the stack frame. They're somewhere. It depends on the structure of the code and how many other variables there are and stuff, where they end up. But in the simplest case, like this very simple code, the A's I put in end up as the 4th value on the stack. So now I control this value and I can write to memory locations. So that's the essence of this. I can now write to arbitrary memory by controlling this format string. All right, let me go back to this stuff. All right, so the most important things to us are %x, and you can put %100x to pad it to 100 characters, because we're going to have to control the total number of characters printed so far to equal the bytes we want to write. And all right, so that's the format strings vulnerability. This is very strange stuff, but C will let you do buffer overflows. And this is the fundamental weakness of C, because it's too close to assembler. So I can set aside room for 10 characters, Then this will copy that string into that string until it's terminating null, and it has all forgotten about that 10, so it goes cheerfully over the 10 without worrying about it, because it's just working like assembler. And so here's the same thing here. There are no arguments to print, but the printf function calls does not know that. That would have happened in previous commands, so it just does its best to print whatever's in the stack without any clue that there's something wrong with it. So now that's information disclosure, and that we've done that. So that's the game read forwards from the stack, and the second one will write 4 numbers to the stack with NNNN, which is not normally what you do, but anyway, we'll do various varieties of this. That's what %n does. So now I can write to a memory location if I can get it in the stack, and the number I write to it is going to be the number of bytes printed so far. So I'm going to have to arrange to waste a whole lot of space making that number the number I want to print. This applies to all of these variants of the printf family. They all have this same feature, that if anywhere the programmer printed just one variable and you control that variable, you can take over the box with a format string vulnerability. So if you want to prevent this stuff, it's actually quite simple, but the defenses that are already out there are not going to do it. We have stack defenses. There's a canary value at the end of a stack frame to notice if you're overflowing the stack frame and getting to the return pointer, and that will stop buffer overflows, but it'll do nothing about this. Address space layout randomization and non-executable stacks will also do nothing, because we are not guessing the address of things on the stack, not at this point. That may come later. The best thing in static code analysis tools, you just look at the source code and look for a printf of only one thing in it that is not, now you can print a static string like hello, and that's fine, but if you print some kind of variable without a format string, it's easy to spot if you just search through the source code. Or you need the assembly code, you can find it, but you have to do static code analysis. Just hunt for that pattern of behavior in your code. I was doing a CTF, and we ran the code in Hopper and made pseudocode, and you could just see this printf hanging out in the middle of it with just one parameter, and that was it. That's the open door you can go through. All right, so here's the exploitation technique, which turned out to be kind of tedious. But so you now control a parameter, so I can now make an arbitrary write to an arbitrary RAM location. To take over the control of the box, I must find a RAM location to write to that will control the instruction pointer. So there are a lot of places to go. So here's the step. First, I have to find a RAM location that will eventually be used to control code execution. Then I have to write a number in there that points to code I was able to inject somewhere. So you're going to have to insert shellcode, find out where it is, and then put that address in some address that's used for execution. All right, so to control the parameter, we got this far before. If you put 4 letters, which is enough for one 32-bit word, before the first %x, you'll find that it goes somewhere on the stack. In the example in your book, it's like 300 words down the stack. In my simple case, it's only 4 words down the stack, which makes it a little more less tedious to write this stuff. But in principle, it's got to be there somewhere, and you can find it. All right, so here's places to put it. You could try to hit the stored return address. It's on the stack somewhere. You could try to run past it and hit that value. One cool thing about this is a canary won't save you, because you're not writing byte, 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 byte to go out the stack. You're just changing that number right past it. So a canary defense won't stop it. Anyway, you could try that, and then what will happen is when it tries to return from a function, it'll hit the wrong stored value and you run your code. The global offset table is a lot easier. That's what we're going to shoot for here. The global offset table, because the code you're using tends to change versions. Your compiler might change version, the library might change version. It turns out that when you call a function like printf, you don't jump right to printf. You jump to a local copy of pointers called the global offset table, which then jumps to another table of pointers, which then jumps to the function. So that the operating system can readjust those pointers if they upgrade the OS and decide to move things around and make them fit differently. And your C compiler can change the address of things so that the two pieces can each have some control to move these pointers around as necessary. But what it means is the global offset table is a series of pointers to all the functions you use, and it's available for your program to write to it. So I can take over execution by just changing the pointer to a function that's called after the exploit. Another thing you could do is mess with the destructors table. In C++, you have object-oriented programming, so when you create something, there is a constructor that makes it, and when you're no longer using it, there's a destructor that tears it down to free up the memory, and you could hijack the destructor, and sort of like the saved return pointer will take over when you return from a subroutine, the destructor routine will be called when the routine ends, and you can hijack code there. And you can also hook any of the C libraries, but we're mostly going to do it through the global offset table. There's something called the @exit structure you can go toward. You can also find any function pointer anywhere in the thing and override it. And in Windows, as we'll do a few weeks out, the structured exception handler turns out to be the cool place to go, especially in earlier versions like Windows XP. This was a set of tables that would handle exceptions that was always at the same memory location. None of the defenses protected it. So if you had a chance to do an arbitrary write, you just right there, then trigger an exception like divide by 0, and an exception handler will now run your code. Anyway, so like I say, let's play with this thing. Remember the source code. Let me go to my live example if I can figure out what's going on here. Escape, there we are. All right, so if I look, I should have 2 windows. Yeah, let's exit here. Quit, all right. All right, I'm gonna go back to this one and I'm gonna look at the source code, which is nanofs.c. Actually just cat. All right, so here's my source code. All right, so this program takes a variable at the command line, copies it into a thing called buff, then there are 2 print commands. First it prints buffer, then it prints a single character, which is a line feed, and that's it. So those are 2 function calls. Once it prints this and once it prints that. So let's see what that looks like in assembly code. If I go here and I GDB that program and I disassemble main, okay, main. All right, this is the prologue. We've talked about this before. The prologue messes with the stack pointer, rounds it off to integral numbers of 16, then subtracts some number from it, which lays aside enough room. So all this is pretty much boilerplate. We really don't care about it, but that's the stack manipulations. The real meat starts happening down here. That's why the first thing I always do is look for things I can recognize. There's a string copy. Remember that was there. It's going to copy a variable. Then there's a printf, and then there's a put char. So this is already pretty much the whole action down here. So this is going to do the string copy. This junk up here finds the one variable and the other variable I'm going to copy into each other. So when you call string copy, it finds a pointer to the source and a pointer to the destination. So these 5 commands together are that one command. String copy this variable, that variable, which is all right. We don't care anyway because that's not where the vulnerability is. The vulnerability is here. This is the printf statement that doesn't have a format string. So it doesn't even really much matter what the code does up here because we can't control it. But here we get a chance to execute an arbitrary write. And after that, it's going to call put char. Now this is kind of cute. They are both called the same function, printf, but the compiler, in its wisdom, chose to implement the first one with the actual printf code, but since the second one was printing only one character, the compiler chose to use this function called put char instead, which is kind of convenient for us because this is the only place put char is used, so all we have to do is hit the global offset table entry for put char, and when it tries to put this character, it'll instead run our code. So that gives us a target to shoot for. All right. Now to find it, we can use obj dump. We talked about this thing before, and I said it's going to be more fun as we go ahead. Obj dump minus R shows you the relocation records for the program. And it's very simple for a simple program like this. Here's printf and string copy. Here's start main. Here's put char and gmod start. There's only 5 external functions used, and this is the one we like. So now we have valuable information. This is the address we're going to try to write to. I'm just going to put it on the board so we've got it for reference. 0804 49, 97 48. All right. That is if we can write a 32-bit word there, then just letting the program run, it will eventually jump to that, thinking it's printing out a character. All right. So now, here's how you write to target RAM, and let's just play with this. You can run, okay, with the dollar signs there, so let me just go into my debugger, which is not there, pardon me. I've got to go here and here. There we are. All right, so I'm in the debugger. Now, I can run the program, and then I can put an argument here, like hello, and it will run and print hello and finish. So that should be expected. Now, I obviously don't want it to just run and finish or run and crash. I want to examine it. This is the call which we are going to use to alter the contents of memory. So the logical thing to do is break before and after that. So I can see what was going on before the exploit, run the exploit, and see what it did. So you could put in these hexadecimal numbers, but it's a lot easier to just work relative. You can break at main plus 59. Right, let's do this. Okay, all right. Do I have to put a star in there just a sec? Do I need to break a star? I do need a star, that's my problem. Okay, let's, I'm gonna quit and come back to clear that. Probably don't really have to, but that's all right. Break star main plus 59. And the next one is main plus 64. There. So now, if I run this thing, and I run it with AAA, it's going to run stop before that. Then when I continue, it's going to continue past it and stop again. And then when I continue again, it's going to print it and finish. So this is the process. Now, to run the exploit, I want to run it. Let's try, for example, with this one. The way you put in a literal thing is with this, dollars and quotes. And now I can put in backslash X. I can put in, well, let me start with this one. %X dot %X. Okay, there's the breakpoint. If I just continue, it continues, and if I continue again, it prints out the same stuff we saw before, a bunch of pointers on the stack. Okay, so now, let me go and follow my plan here. I wanted to inject this stuff to try to write to that location. So that's the game. Let me see if I can construct it, and then I'll check it. It's run. To put in literal hex values, you use dollars and quotes. So it is that number backwards. So I have to put in 48, 97, 04, 08. So it's 48, 97, 04, 08. That's what takes the place of the AAAA. Now, if I just want to see if it's working, before I go any further, I just want to see if that ended up on the stack okay. So I'm going to do %, I'm going to do dot %X, dot %X, dot %X, dot %X. See how that looks. And then continue. Continue again. Okay, there it is, 8008, the 0 is neglected, 04, 97, 48. So the fourth word on the stack now contains the address I want to write to, so that's good. So if I want to write there, all I have to do is repeat the same thing I just did and change that to an N. And it will write to that address. So let's see if that works. Now, in order to see if it wrote to that address, I should examine the memory near that address. I'll examine 4 hexadecimal words at that address. And that address is just this number here. I can copy and paste it. And I have to put a 0x in front of it. Okay, so there, this is the pointer to the real putS function. And my idea is my attack here will change that pointer. So if I view it again, it's changed it, and it's changed it to 1C, which is just 30 or some random number. That's the number of bytes I printed so far. Remember, one problem is I haven't been able to control the value I write there, but I have controlled the location I write to. So now I can control a pointer which will eventually be used. So now I've ruined this program. It's going to crash. When it tries to print, it's going to try to run a memory at location 0001C, which is crazy, way down in kernel memory, where it's certainly not authorized. So if I continue, it's going to get a seg fault, again, as I try to access a memory I can't get to. So now we have to control that value and put in something less stupid than a 001C. So here's Python code to write one word. We're going to need a better system than just putting numbers in one line there. We're going to have to build it. So let's start with Python here, and I did this with f1.py. I've got these ready to go. So let me go here and nano f1.py. Okay, so this one here, this is that same number, 08, 04, 97, 48. Then I have the %x, 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 %n. You put those two together, and that's the attack. It's the same thing I just put in there. I put in a few extra dots to make it read. So this should write random junk on there. Now, the way you execute that, you make that code executable with /mode +x, and you run $f1.py like this. The dollars with the parentheses will run the program, take the output, and put the output in the bash command line. as part of the command. So that should do it. It says I'm restarting a program with different parameters, which is expected. So before the breakpoint, I can examine my memory. And that's the real address, 804,000 that really goes to something. Now I continue and examine it again, and now it contains 18, which is a stupid number. It's not the same number as before because I had some dots in there, so I'm printing more characters. But now that's worked, so now this of course will crash if I continue, but that's not the interesting point. The point is now I have an attack where I can write to the right place, and it's in Python, so I can mess with it. So let me see, I may not need to refer to my slides for a while. I've got a whole series of these. Before I jumped kind of quickly to the solution, but this time I just redid it again because of course the version of Kali has changed and so the details are different, and I did it in smaller steps, which made more sense to me. In general, there's a fundamental rule of programming, which is always do just a little bit and then check it. If you write a page of stuff, it will crash and you'll be lost. Where are the 4 errors on this page? So especially when you're with this hacking stuff or you're doing something bizarre that's not intended, that's not in the books, it's best to take small steps. So my next idea was to try to write 4 words. So I took this word at 48 and I just moved forward 4 bytes to 4C, 50, and 54. So now I have 4 words. And I'm going to print, see this one is the 4th item on the stack. Remember we found that out. Whatever I put at the start is going to be the 4th item. So the next one will now be word 5 in the stack, and 6 and 7. So these will be 4, 5, 6, and 7. So I can have %x, 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 %n. This will write to the 4th address on the stack. This will write to the 5th address on the stack, the 6th and the 7th. I can write 4 words. And they should just line right up there so I'll see them. That was my plan. That's F2. So if I go back here and I run this thing for F2, then I'll start again from the beginning. Here's the breakpoint. I'm going to examine those 4 words. That's before we mess with them. Now I continue. Now after we mess with them, you can see I wrote 24 here and 24 here and 24 here and 24 here. So I did manage to write 4 times. Now I'm not controlling the value very much, but at least, okay, so this is actually kind of pointless, right? I took making a bunch of invalid addresses that'll crash the program. So the next step is to write those so they overlap. See, how I really need to write a 32-bit word that is not all full of zeros, something that points to a real address of code, probably more or less close to that thing there, 804.836, something that really goes to real code. So let's try the next one, which is F3. So this time I just changed these numbers to 48, 49, 4A, and 4B. Each one of the writes will write 32 bits, but I'm gonna, this is kind of nuts, but it works. I've got 48, 49, 50, and 51. Here, let me turn on the lights up here. Okay, I got these 4 bytes. So on the first one, I'm going to write here, say values in A. Then the next one's going to start here and write B, 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 B. Next one's going to write here. The next one is going to write here. So with 4 32-bit writes, I can put arbitrary values in these 4 bytes and have 3 bytes of collateral damage. Some other memory location is going to get clobbered, but I don't care. The word I want can be turned in any byte I want with 4 overlapping writes. And that's what we're going to do. So by lining them up like this, when I run that one, which is 3, it's going to collapse these 4 24s all into one word. So I run it again, I look at the contents of memory and continue, and then look at the contents of memory again, and now I got 24, 24, 24, 24 in one word, because I just squished those 4 writes together. So I'm writing the same thing everywhere, but now I have 4 writes that write 1 byte each, and after those 4 writes I can put anything I want in that memory location. So, we just have to refine this a little more. Look at F4. All right, so now, in order to control the number, I can't just write them one after another or they'll all be the same number. So I have to space them out. So now, after each one of these, I put 4 letters, and I just put junk. Any 4 letters will do, because now this number is word 4, the word 5 is junk, word 6 is the next one, word 7 is junk, so now I've spaced them out. Instead of being 4, 5, 6, and 7, it's 4, 6, 8, and 10. This is important because I need something in between them so I can control the value. And now the form is now 3% x's and a percent n, and now percent xn, percent xn, percent xn, where the x's are going to print out the junk. If I didn't have them, I'd be stuck putting the same byte in all 4 places like I was before. So let's see what this one does. It's this thing, all right. So this one is F4. Run it from the beginning, and look at this value and continue, and look at that value again. Okay, now I have got 34, 3C, 44, and 4C, because after I write the first byte, I then write junk, which causes more bytes to be printed, so it increments the total number of bytes from 34 to 3C. Apparently it's taking 8 bytes to do that, which makes sense because it's 1 pointer. So it takes 8 bytes to print out a 32-bit word in hexadecimal, because it's 2 bytes for 2 characters for every byte. So 34 is the first number. Then I printed junk in hexadecimal form, which took 8 characters. So this is now 3C characters printed. This is 8 again, 44, and 4C is the next step up. So now I'm able to get different numbers in each byte. And now I just need to modify it so I control the numbers in each byte. And that takes a few more steps. So next one is F5. All right, so here, I'm going to just put 16 in after each one. I'm going to see if I can jump by 16s instead of jumping by 8. So remember before, if you put %x, it's just going to print a hexadecimal value, which is usually going to be 8 bytes long, but it might sometimes be 7 or 6 if things are starting with 0 and the zeros are dropped. But if you put a 16x, it will always be 16 bytes long, 16 characters long on the screen. It'll pad with spaces. So I'm going to pad each one of these to be 16 characters exactly. And so when I run that one, which is F5, which should be here, now I get 3E, 4E, 5E, 6E. So now I'm making it jump forward by 16 every time. And as you can see, by just changing those 16s to other numbers, I can get anything I want here. And that's how this works. So let's take a look at the next one. I tried to jump right to the end at this point, and it totally failed. So I went back to doing 1 step at a time. It's always much faster not to rush, but stay in control. It's easy to get frustrated and jump to the end, and usually it's pointless. So next one I said, well, this writes the 3E. Now I'm going to write, let me get my slide, because I had a plan to explain all this. So what we've done, we wrote 1 word, then we wrote 4 words all the same. That was the 24, 24, 24, 24. Then I collapsed it and wrote 4 bytes, all the same, into 1 word. So we're moving in small steps towards the goal. Now I write 4 bytes with an increment of 8. And now I write 4 bytes with an increment of 16. All right. Now, the next thing I want to do, which is F6, is write a 0 in the first byte. So, consider what we had before. I can go back to my demo now. All right. What we had here was, we have now written a 3E into there. Okay. So if we want to write a 0 into there, we have to change the number of characters printed so far to a different number. Now, we can't take the number of characters printed so far down below 3E, down to like 0. All we can do is go up. If you have to go up to 256, which will wrap around, and the low byte will be 0. So to hit 0, we need to add 256 to it, and then take away the 3E. It was 16. 16 produced the 3E. So if I add 256 and take away 3E, it should produce 0. So my goal here is just to hit 0 in the right-hand byte. And all right, that's the plan. And I think that's F6. All right. I continue, and I will look at it again. And now I have 0 in the right-hand byte. The next one is now 8 instead of 4E or whatever it is, because it was 256, which wrapped around to 0. So now I've got a 0 here. That's good. So now I can just add more to it and get any byte I want there. But whatever I put in there affects the later bytes because it's a running total of all the bytes printed. So however many bytes you put in the first place are going to also count in the second place. So you have to keep rolling over at 256. All right, so that is number F6. If I look at F7, this is where I decide to hit the second byte. This is where I just make it hit an arbitrary byte. Instead of hitting 0, I'm going to hit a byte of A1. I made it 41, which is a capital A, just so I can see it. So now I add this. What I had before plus A1, now I can hit an arbitrary byte in the last byte. So it's going to be A1. So that's a small change, but important. So now I'll get an A in the last byte. And so now I have a 41 there, so now I know I can control that and put any byte I want. So next thing is to get to the next byte. I, of course, tried to jump all 4 and it turned into a mess. One step at a time is much more effective. All right, so now that I've got the first byte doing what I want to put a desired byte in the second one. And so what I have to do is add another 256 to wrap around another time, and then subtract N1, because however many bytes I wrote to make the first number, I have to take it away. This will get me to 0, and then I add A2. That's the plan. So this is the math to make the second byte. So now the first byte should be 41, and the second byte should be 42, if I've got it right. So that's this one, F8, yes, examine, continue, and examine. And now I get a 41 and a 42. So we're on the road. And at this point, I think I finally was able to convince myself the pattern was clear and go to the end. Let's see F9. Yeah, and get all 4 bytes. So here's the game. You start with these things, you eventually write to, then you have 4 desired bytes, 41, 42, 43, and 44, just so I can see them. And here's the pattern. This one you have to take N1 plus A2, or I have to take N1 and N2 plus A3, so I'm going to need 3 256s to make sure that's always a positive number. And this one I'm going to need 4 256s to take away the number of bytes I wrote the first time, second time, and third time, and add A4. So this is the pattern. And those 4 writes will now put A, B, C, D in the pointer. So that's F9. And let's run that one. F9. All right. Examine it. Continue. And this time, for some reason, it printed out stuff, but I'm not too worried about that. Now I did get the A, B, C, D to run there. So now I have an arbitrary write. I can write to any RAM location, and I can put any value I want in there. So now it's a simple exercise to continue from here. Now I don't have it all live because since things changed, this is as far as I got with my new one, was to get the arbitrary write, but it's also a logical spot to stop. Once you can write a chosen word, then the process of exploitation is simple, and you've been doing it in the other projects, like the simple buffer overflow and such. So you have this code that lets you write an arbitrary value here, and this time I put AA, BB, CC, DD, when I did before, just to choose something to see there. So since I can do that, now I have to put in shellcode. Now, so my exploit, remember the exploit that does this is these W things, which are the addresses, 1, 2, 3, and 4. Then the form thing, which is all this %x, %n stuff, that's the stuff that actually does the format string exploitation. However, all this stuff is going on the stack. Remember, the AAA went to the 4th element on the stack, and all these other things are just piling on the stack. I got to inject shellcode somewhere. And the logical thing is just put it on the stack after all this. In the same, so I can put more junk out here, and it will be on the stack. And that's where I'm going to put my exploit. So I'm going to put out there a NOP sled and shellcode. It is a good practice to pick a size for your exploit and keep it always the same. In this case, the program is so simple it doesn't matter, but in general, it's good practice. So here's what I'm going to have 100 bytes of NOP sled and 250 bytes of shellcode. Now, I don't need real shellcode yet. I can just use CC. CC is an interrupt 3. When the program hits CC, it will stop, and I can tell that it made it to that point. So this is a fake shellcode just to see it work. and I just add it to the end. So you do all this junk which exploits it, then you have NOP/SLED and shellcode. Now you run it, and you break, at the breakpoint you break it. So if you do the examine we were doing before, where you examine just 4 bytes, or 4 words, you'll see that the putchar global offset table now has AABBCCDD. So that just shows I haven't broken anything. My original exploit that did that right is still there. But now you can examine the stack, and this is a good thing to know, x/any number x ESP. This will show me the stack right from the start up. So there's the ESP. So up here I've got all this junk I put in, and down here you can spot the 90-90-90-90. That's the NOP/SLED, and down here's the CCCCs. That's where my shellcode's going to go, so it's all just sitting on the stack. See, I injected AABBCCDD, and I needed to know what address to put there, and now I know. I just have to hit any address in this NOP/SLED. So pick an address here that will work. Remember, since ultimately this stuff is treated as a string in C, you can't use zeros. So choose an address that doesn't have 0, and that's what I should be writing in. So instead of AABBCCDD, I should be putting in something like BFFFEEE0 to hit the NOPs, and then it'll run my egg. So here's what I planned, was BFFFEF10, one of the values down at the end of the NOP/SLED. That would work. All right, so if you put that value in, it runs, and when I break, so I change the code to put out that value. Then when I examine it, it puts, this is before the exploit. After the exploit, it puts BFFFEF10 in there. And when I continue, it now runs to the NOP/SLED, and it hits a breakpoint here at EF45. And if you go back up, you'll see the EF45 is where the first CC was. So it worked. I hit the NOP/SLED, it slid down the NOP/SLED and hit this, and that's what I wanted to see. So now there's another step, which I skipped when I was beginning this, which frustrated me greatly. Before you go any further, you have to test for bad characters. Bad characters are very, very annoying. So I put in shellcode up there in Python. I just put in all the bytes from 1 to 256. I already know 0 is no good. 0 will terminate a string, and whatever's after that will never be entered in the RAM. So I have to try all the bytes and see what gets there. So instead of the CC, I just put in 256 bytes of shellcode. And what I found was it put in the 1, then it put in 2, 3, 4, 5, 6, 7, 8, and stopped. That's because 9 is a tab character, and a tab character is interpreted by C in the command line where it's going as a separator. So 9 is forbidden. And now I don't know what else is forbidden. You only find up to a block. After that, it's gone. So now I have to do it again, starting at 9, starting at 10 rather. So now I make another one that injects from 10 to 256, and I look for that down here. I've got, here's 11. I'm losing my mind. Yeah, 16 is bad, but 10 should be good, so I am not seeing it. That injected junk after the 90s should come readable stuff that I cannot see.
So that's like decimal 10, not hex.
That's decimal 10, yes, so it should be 0A. So I should have seen a 0A down there somewhere, and I am not seeing it.
0A is new line though.
It is, so I think 0A was also bad. That's right, that's right. So nothing got up there because the 0A is also bad. Okay, good. That's right, so now I have to start at 0B. So there's a mistake in my slide. This is not just, I'm catching up to you there. This should just say 10. Okay, good. 10 is bad, 9 is bad, and 10 is bad. Okay, thank you. Good. So now I have to start at 11. When I start at 11, it will actually put in, I see some 1C, 1D, 1E, 1F up here. So before that, there should be over here, 10, 11, 12. There we are, C, D, E, F. I started at B, and the B, I'm having, here's the B. Okay, here's the NOP/SLED of 90s. The B is over here, 90, 90, 90B. Remember, everything is backwards. You go right to left in each byte. So the B is here. Then C, D, E, F, 10, 11, 12, 13, 14, 15. So a bunch of characters are good. I got up to 1B there, and 1 C, D, E, F, and that's it. The 20 never made it, because 20 is space. So you could use logic, but experiment is much more reliable. Just try it all. So now I know another bad character. And if I start at 21, finally, they all go in. All the characters from 21 to 255 are okay. So in this case, since it's just a bash command line, it's the logical stuff. Space, tab, line feed, and new line, only bad character, and 0. So, all right, so that's the game. So now to generate shellcode, you can use MSF, Venom, and you can specify the bad characters, 0, 9, A, and 20. And this will create a shell that just starts listening, dodging all those characters, and put it in Python. And the prepend fork will cause it to fork into a new process, so that even if the original process crashes and burns, it won't kill the shellcode. That was what I did. That creates this Python code, which is not too long. And so MSF Venom writes this buffer command, and now I set aside 250 spaces for it. So I take 250, I put my 4 pointers, and then the format string. This is the attack. Then I put in an op sled. Then I put in the buffer, and then I just put in enough X's to make the total length stay the same, which is just a good practice, although it doesn't really matter here. And that should do it. I've already arranged that this exploit will redirect execution to in the op sled, which will then run down here and run the egg that came from Metasploit. And that's what does it. So now the shellcode gets there intact. When you run it and pause it, you'll see all the 90s, and then you'll see this junk go, and you can spot it here. The end of this thing is A8B1, and here's the A8B1 getting in there. If you had a bad character, the injected code would not be complete. You'd be missing the end of it, and that's one way to test it. So that means when you continue, it will now just start listening on port 4444, and you can connect. Now, one very irritating, dirty trick, when you get it working in the debugger, it will often fail outside the debugger because the debugger is not perfect and it can be off by 20 or 30 bytes. But I think this one, that's why the NOP sled really helps. If your NOP sled is a couple hundred bytes, you're more likely to have it work outside the debugger. If not, the simplest thing is just trial and error. Add 10, add 20, add 30, subtract 10, subtract 20, subtract 30. But it takes a little while to be that confident. The nicer CTFs, and some of my projects have been rewritten this way, just print out a pointer in the program so you can see, and then you can run it in GDB and see an address and run it out of GB and see how much changed. But that's a lot. Anyway, that's what I wanted to show you. And of course, you got to do it in the homework. So you're going to do the buffer overflow without shellcode we talked about. The buffer overflow shellcode is simple enough, and on you go. Down here, project 6, you'll be doing just this thing with a format string, and you get to see it go. If you're interested, there is a shorter, smarter way to do it. Mentioned in the book, by using, I think, %HN, you can write 16 bits at a time. And supposedly, then you don't have to do this 4 overlapping write thing. You can write directly the whole 32-bit word with one format string exploit, but it amounts to the same thing in the end. And that's what I wanted to show you. Got any questions about anything? Yeah.
So if we're doing randomization, memory allocations, and that kind of stuff, is this all getting resolved at runtime? Is that what's happening?
No, if the memory, if you have address space layout randomization, then we're going to have the format string exploit will work, but you won't know what address to put there, and that's a problem. So to defeat that, I mean, there's for every defense, there's a countermeasure. Address space layout randomization makes this kind of exploit harder. There are 2 solutions. One is, in fact, on Windows machines, there's 2 weaknesses. ASLR is not turned on for every process. So you can just exploit a process that doesn't have it. That's the simple way out. The second thing is, when it is there, they didn't put enough randomness in it. I couldn't believe they didn't just pick a random location. They only changed the high order bits. So there's really only like 8 bits of entropy or 12 bits of entropy. So if you just run the attack 1,000 times, you'll get lucky. Another way to do it, which we'll do in a later project, is the heap spray. That's the big one. You write JavaScript, what you do, you make your exploit have a really large NOP sled, like 10,000 bytes. And then you put it in a browser and run JavaScript, so it just puts copies of it everywhere, and so it fills up all the RAM. Then just jump at random, because you made it so 99% of the RAM consists of NOP sleds, and you have a very high chance of hitting one and running one copy of your exploit. That's another way to defeat ASLR. Data execution prevention is a deeper problem. Data execution prevention means that even when you've put it on the stack and jump to it, it won't run because the stack is not executable. And we'll fix that one later. The cure for that is to turn off DEP, obviously, but you have to turn it off while it's on. So what you have to do is return-oriented programming, where you have library code from Microsoft sitting in memory, and you want to make a sequence of perhaps 40 or 50 machine language instructions that will turn off DEP. So you need something to load like 1 in an accumulator, and then load 2 in this accumulator, and then jump to do an index 80. So you find some code that does one little bit and then returns, and then the code does one more little bit and returns, and you paste them together, like building a message out of words you cut out of the newspaper. That's return-oriented programming, which sounds insane, but it's possible now because of Mona, an immunity plugin that does it. It used to take a long time to do it. So you can actually piece together code that's already there, and so you don't inject any code, you just inject a series of values that control the instruction pointer. Go here and return, go here and return, go here and return. No code I put in is executing. The code that's already executable is running, and the end result is to turn off DEP, and now I can run my exploit. And that works pretty well. The latest version of Windows is supposed to have the new defense against that, which is Microsoft will have in the libraries a list of the acceptable exports, and you are not allowed to, if you have a routine that is 500 bytes long, you are not allowed to jump to byte 490 anymore. You have to enter it at byte 10 where they want you to enter, and it will not let you jump to any other byte, which is pretty smart actually. And I don't know why it wasn't always that way, but that was the defense they got from the Blue Hat conference. So, you know, Microsoft has more and more clever defenses. And of course, more and more motivated attackers climbing over them. But that's what we'll do as we go ahead. So we're doing the simple ones now, and we'll turn on the bells and whistles in later projects.
We're going to do anything with relative addressing?
Sure. I mean, this is all relative, but you can't jump to relative addresses. We will do some. There's one later where you jump over some things. That's coming up. That's a short jump. Yeah. Any others? All right. Well, let me stop this recording. All that stuff is coming, but give it a shot in the project. So I'll go to the lab and help anybody that wants help there. This is 127, chapter 4, I think.